All right, so let's have an actual lecture now. So let us scoot on down here. We're going to learn about computers today, guys. So yeah, you had to get through like 2 or 3 classes to be ready for this, but now is the time. All right, so here's the simple definition of what's inside of a computer, right? Stuff that you should know by now, but we're going to definitely go further than this. So here is like middle school definition of a computer. You got in this box, right? There's the actual computer part. You've got the CPU, right? That's like the brain. That's a piece that's living in there. It's doing the thinking, right? We think of it that way. And then you have memory, or RAM, random access memory, inside of your computer somewhere. A few sticks of that maybe. And that's where you store information for later, which is honestly it's a flawed metaphor to say these things, because as humans, our memory is in our brain. So but in a computer, it's separate. You got the CPU doing the number crunching, and then to save things for later, that's the RAM. That's the memory, the main memory. All right, so you got that. You got input and output devices, of course, like a mouse and a keyboard. Those are input devices. Monitors and printers and speakers, those are output devices for you getting information from the computer. And then you have I/O devices, which are short for input-output devices, things that can do both. You can read from it, and write to it. Those are like your hard drives, like your SSDs, your spinning hard drives, flash drives, stuff like that, inside of the computer as well. So those are all the things you should probably know by now. But of course, we're going deeper than that in this class. Okay, so let's zoom in on the CPU and the RAM. Like this is kind of where we're going in this class. Eventually, you'll be able to understand diagrams similar to this one. But like here's the processor. Here's how it's interacting with the RAM. It's connected along what's called a bus. Got some fun metaphors to learn soon, I promise. So yeah, let's talk about these things. Let's slowly zoom in. Okay, that's where we're going. So for example, when you run a program, like you double click your program, or you like / hit enter on the terminal, your program gets loaded into memory. In order to run a program, it needs to get loaded into main memory. So like all these programs running on my computer right now, taking up over half of my memory, all these things running in my task manager, they are loaded into RAM right now. That's the only way that they can run. Okay, they are, yes, on the hard drive, but all that stuff is getting, like the program itself is being copied from the hard drive of my computer into RAM, and that's where it gets run. Okay, that's much faster that way. Okay, so what is memory? Let's go back to like CSCI 40, CSCI 41. What is memory? How did we think of it back then? Memory is just a big long table, right? It's a big table. As programmers, we think of it as a table that maps addresses to values. Yeah, so like the starting address is 0. It's an unsigned number, right? So starting address is 0. That's the first address you could possibly put something at, but we like to use that as the null address, so you're never supposed to put stuff there. That'll give you a seg fault. Then you have like address 1, address 2, ... And that's where you store stuff. So every address can hold a single byte of data. All right, so all memory is, as programmers, we think of it as a huge table that maps addresses, where the thing is, where the information is, to bytes of data, things that we're storing at that address. So like you can store the number 42 at address 1. Or you can double up, like you can use a couple addresses to store a variable, because ints, for example, are 4 bytes long. Okay, so you can use like starting at address 1, taking up addresses 1, 2, 3, and 4 is the int x, for example. We can do that. So that's a thing. There's more to it than just RAM and hard drives. If you've built a CPU, not if you've built a CPU. If you've built your own computer, you have probably heard these words before. But there's also what are called caches. It's a French word. If you haven't seen it before, this word is called caching. That's how you pronounce it. There's things called L1 caches, L2 caches. Those just make things faster for us. It's pretty nice. So we'll get into that soon. But yeah, so the memory, like here's that, it's connected to the processor. All right, it's connected to the processor because when you load a program or when you run a program, it has to run, like the CPU does the thinking, but the program is getting loaded into memory, like the code as well as the variables and data. Okay, so it's all going to memory, and the CPU needs to read from memory and write to it. That's essentially how a program executes. Yeah, it's just a big long sequence of messing with memory. Essentially, that's all a program is, right? So yeah, so that's how that works. And so in memory, in addition to your variables, there are like your return 0. That's somewhere in RAM. The code itself is somewhere in RAM as well. And we call small bits of code, like a return 0 line, maybe, we call those instructions. All right. So what the CPU does is it loads one instruction, a thing called an instruction, at a time, and it runs that instruction. Okay. I don't expect you to understand this. I haven't really defined what instruction is yet. We'll get there when we start learning more about assembly. Okay. But essentially, instruction is one CPU thing, one thing that the CPU can run immediately. All right, it's the smallest amount of information that the CPU can like take and roll with in one clock cycle. So there's another term. All right, so it takes about a clock cycle to do it, and this is the smallest granularity of time inside of a CPU. It's like how fast can it do something? We ask it in terms of clock cycles. How fast a CPU can run an instruction, we say, is one clock cycle. All right, so it's like the CPU's got a little clock it's ticking, and it takes that amount of time to execute an instruction like a return 0. Okay, so just think of it that way. I promise I will explain further, but it's going to be a bit vague right now. Okay, so again, both instructions and data, like your variables as well as the code itself, they live in memory, just separate bits. That's all. So that's all that, and it takes clock cycles to run your code, to run all those instructions. All right. And so if you've bought a CPU or you've like bought a computer, you've probably seen like this term, like this processor runs at 4 gigahertz. And that has to do with instructions and clock cycles. So if you have a processor that's a 4 gigahertz processor, what that means is you can run 4 billion instructions per second. That's the idea. Okay? So yeah, a clock cycle is like one 4 billionth of a second. That's kind of what that's saying. All right, and every instruction, like that's the smallest thing that it can run in one clock cycle. That gives way to this kind of data, that kind of thing that you use when you're buying something. Okay, so I don't expect that to make a whole lot of sense. Only once we get into assembly will it become clear. But just put up with me right now. I promise we're getting there. Okay, so yeah, if nothing else, if you take nothing else away from this slide, the key idea of like computer science, all it is deep down, if you think about it, is like if you're programming, you're writing a program, all it is just moving around values. You're messing with stuff in memory. All right, moving stuff from this memory table to the CPU and back, and like changing things. All you're doing is messing with memory using the CPU, and that does cool stuff. Right, that's all your program is. Okay, that's this. I swear. Just like even to print stuff to the screen, all it is like talking to a special place in memory. It's really weird like that. We'll get into it, but this is all programming is at the end of the day. It's a weird thing to realize, but yeah, now's the time for you to know, I guess. All right, so let's get some assembly today. All right, we're getting there slowly. We're going to use ARM processors in this class. Our class server uses an ARM processor. And let's talk about that. So you have different CPUs, all right? Different CPUs have what are called different instruction set architectures, all right? Different CPUs, maybe I should say like have different instruction set architectures, or ISAs, all right? And what an instruction set architecture is just a big long list. It's all the instructions, again, that term, the CPU knows how to handle. So like there's an instruction for returning from a function. There's an instruction for adding numbers, okay? Stuff like that. So different ISAs know how to do different things, okay? So ARM processors can do different things to Intel processors. They have a lot in common, but they do have some differences, okay? So in this class, what we'll work with is 64-bit ARM processors, all right? It's a useful thing to know. We'll learn that kind of assembly. It's useful because like almost certainly, like you have a smartphone, right, these days. Pretty much all of you have a smartphone or like a tablet or something like that, or a game console like a Switch or something. Every single one of you who has one of those things is using an ARM processor. All those things, all those small devices, ARM devices are really good. ARM processors are really good on power usage. And so that's why all the small things are using them, okay? So you have an ARM processor, or you've interacted with one for sure by now, okay? So this is the first ARM processor. The very first one is that was actually like a success. There might have been some before, but the BBC Micro, built in 1981, was the first like commercial successful use of an ARM processor. It was battling against Intel back then, like it is now. All right, and ARM, it used to stand for something cute. It used to stand for Acorn RISC Machines, or Acorn RISC Machine, and they later thought that that wasn't cool enough. I honestly like the Acorn because like there's a little acorn right there that they put on their little motherboards, and they sadly thought that that wasn't cool enough, and so they changed their ARM. ARM used to stand for this, and now it stands for Advanced RISC Machines. I'll teach you what RISC means later, but yeah, that's what ARM means, and that's what we're going to focus on in this class. Intel processors, like the main competitor to ARM processors, use an instruction set architecture called x86. Okay, so that's what they're doing, and that's the other major one that if you have like a Windows laptop or desktop, for example, that's what's in there. So like this computer that I'm using right now has an Intel x86 processor using an x86 instruction set architecture. That's how it's being talked to in every program. Okay, so yeah, the class server, obviously, if we're gonna learn ARM stuff, the class server is running an ARM processor. Right? Our class server is a 64-bit ARM machine in the cloud. It's actually in Germany. That's the closest place where I could get one. It has an ARM v8 processor, if that is useful knowledge to you, and it runs 64-bit Ubuntu Linux. All right, so that's what we're using in this class. And if you'd like to play around on your own with an ARM machine, Macs these days use an ARM processor. They have their own, and then also Raspberry Pis. Those are like these cute little things. Those have ARM processors, and they're pretty popular. All right, so yeah, that's a little bit about our class server. You're going to do all your programming assignments. You have to turn them in on the class server at least. You can do the work on your own computer if you want, or you can do all the work on the class server. Doesn't matter. But I've made you all accounts. They do not become active until the first day of the semester. So if you're watching this video a little bit early, they're not ready yet. But I'll walk you through how to get into the server on the first day of class, and onward it will be ready for you. Okay, so yeah, we're ready for assembly. Are you ready? We can do this. The first thing I want to do is teach you like the simplest assembly program, and to get there we have to build up some knowledge, all right, or at least review some stuff one way or another. I would like to make as our first assembly program a program that just exits immediately, that like gives control back to the terminal, just does nothing, stops itself. So that's where we're going. And how do we stop a program? Like, what's the simplest program that just exits in C++? It's one that just like returns 0 from main. It's like, what does that mean? I make this code. What do I want to call this? Return from main.cpp. If I just have this program that returns 0 immediately, what is that? Like, what does the 0 mean? Do we remember? Have we been taught this before? So yeah, what main does, like the reason it returns an int, the reason it's not void main, the reason it's int main, is because that thing that you return is meant to be an exit code. All right, it's meant to be an exit code, and that exit code tells the terminal, or whoever ran that program, is usually the terminal that's starting it, right? It tells whoever ran the program, if that program did its job correctly, successfully, if it ended successfully. So 0 means, yes, it did. 0 means, yeah, that program ran perfectly, no issues. And if you return any non-zero number, that's meant to mean, oh no, something horrible went wrong. And you're supposed to like go look up the code. There's no standardization. It's just like non-zero numbers mean bad things. Go look up in the manual of the program what that code means. Okay? So yeah, let's talk about this. So this is the exit code that gets returned back to the terminal. That's cool, useful knowledge. And yeah, I'll show you how to view that exit code. I promise the terminal gets it. I'll show you how to look at it. We're going to compile the program with G++. That's what we're going to do. All right, so I'll say G++, return from main.cpp. And if you say nothing, if you give nothing else, it'll make a file called a.out. That's like the default name for running a program. But if you want to be cool, you can say, no, call that file something normal sounding. Let's just call it return from main without any extensions. So now that made the file return from main, which I can then go and run, /return from main. Voila, it did nothing at all. Okay, oops, that's supposed to be exit. So I ran the program. The terminal saw that return code, that exit code. Here's how you look at it. You say it gets shoved into a special terminal variable called $? Which is a fun thing. And to look at its value, you can say echo. It's a terminal command called echo that'll just like take what you give it and print it out. And so it'll look up the variable and print out the variable's value. So that $? is a terminal level variable that gives you access to the previous program's exit code. Okay, so that's pretty cool. So I can say echo $? And what do you know? It's 0. And you can change this return code. Change it to 42. Recompile. Rerun. And some terminals are like, oh, non-zero exit code. I'm going to make your terminal prompt red instead of green now, which is kind of cute. But now, of course, it sees 42 is non-zero. It's meant to mean issues happened. Issues occurred. Errors. So yeah, there's that. Let us next talk about like, okay, G++, that's the compiler we're using in this class. What does it mean to compile something? Again, we're getting to assembly, I promise. But we have to go through the compiler right now. So, because secretly G++ is creating assembly language. It's doing it for us. So, all right, at a high level, what a compiler does, if you want to be very, very precise in your words, the job of a compiler is to make object code from a single source file. So you give, if our compiler is G++, you give it this return from main.cpp file. You give that to the compiler, G++. It spits out for you in what's called object code. It's machine code for that single file. It's not yet runnable. It's like return from main.o or something. .o for object code. So I'll call this return.o. So that's the job of a compiler. It's meant to make this. Just like make machine code for that one file is not yet ready to run. Okay? For a single source file. You might have to run it a bunch of times if you have a bunch of source files in your program. So that's the real job of a compiler. All right? The lines get a little bit blurred because G++ secretly runs the linker as well. All right? But it's really a two-step process. So the linker is a piece of code. It's a program that combines a bunch of pieces of machine code into a final executable, runnable program. All right, so the linker's job, which is sadly also called G++ for us, G++ is doing both for us, is to take this as well as any other object code that we've made for our files, combine it with all the libraries that we need to use, like IOStream, for example. It's been pre-compiled. It's got object code for that, for cout and all that. Okay, all that stuff gets linked with our stuff, and then all right, then the program knows where everything is, and then the linker is able to spit out a final runnable program like a.out or something if you don't give an actual file name. Okay, so G++ sadly does the job of both, so the lines get a little bit blurred, but really G++ is secretly running the linker, and the linker's name is on a Linux machine is called LD, right? So you can see all the little things that G++ is sweeping under the rug and doing for us by saying G++ -v when we're compiling. -v stands for be verbose, like be extra wordy, verbose. So let's do that. Let's say G++, all this stuff, but -v at the start. All right, so that spits out a bunch of cool stuff. We can't see it all, so let's save that into a file. I'll call that file g++-v.text. So make a little text file with that information. So this is what G++ is doing for us. It's giving us all the steps. It's being very verbose about it. Okay. So here is the call to the actual compiler. It's called CC1+. It's got a funny name, right? But it's getting that one source file. You see it right there? Getting that one source file, and it's putting it into a temporary place, right? A temporary place. And then that's the job of a compiler. It's meant to make object code, and the reason it does it, the way it makes object code, is first it converts your C++ code to assembly code. All right, that's the secret. So the job of a compiler is, yes, to make object code, but it's a two-step process itself. It really makes assembly code. It makes assembly code, and then it gives that assembly code to the assembler. It's called AS, the assembler. So it takes the assembly file, creates the object code. So that is the two-step process of a compiler. All right, and then it's all getting linked together, and the linker is being called from this thing called collect2. It's a little weird, but it's there. It's all there. All right, if you want to check. So that's what G++ is doing. The compiler's part is creating. Maybe we should write this. The job of the compiler. Compilers. I don't know. Create assembly code, and then assemble it. Into machine code. I promise these words will make sense soon. But that's essentially the job of a compiler. It's a two-step process. To make object code, you first need to make assembly. Go from a CPP file to an assembly file, which for weird reasons is a .s file, and then take that assembly code file and make a .o file out of it. All right, that's the .s to .o. All right, so that's the job of a compiler, and then you link it all together. All right, that's probably way too much information, but the reason we do this is, oh sorry, it's not ARM32 anymore, it's ARM64. I knew there was one spot where I didn't change it. Now we're finally ready to go to assembly. All right, so we've just discovered that the job of the compiler is to go from our high-level C++ code to assembly. That's part of it. We can get that output. We can look at assembly for the first time with G++ -S. So let's do that. Say G++ -S on our file. G++ -S on our return from main.cpp file. So this bad boy. What does this look like in assembly? How did G++ do it? Let's watch. So if you hit enter, this creates return from main.s. So .s is short. .s means it's an assembly file. For some reason it's s. .a was taken, I think. .a means like archive, so it's s. It's the next character. That means assembly. And so this return 42 program, let's see if I can split screen it, gets turned into this assembly code, return from main.s. This is assembly code. It's a little disgusting. It's very low level. But if you scroll down, you can eventually find the main function. Here's the main function. And then here's the number 42. It's being moved into a place. And then ret for return. Like, there's the main function. You see it? Does it make sense? It's a little weird. They got a bunch of other weird stuff that's just like compiler specific. It's doing some extra fancy things. But this is essentially the assembly. This is CPU instructions. That's the lowest level you can go. Isn't that fun? So that's assembly code. Let's see, is there anything I want to show you? I think that's it. That's what I want to talk about. How fun is that? Like that's it. That's where we're going. All right. So let's make our own version of that. All right. We have to roll it all ourselves. Okay. We have to do it all ourselves. So let's make a program that returns a value of our choosing as the exit code in 64-bit ARM assembly. It's great. All right. This is like our hello world essentially of assembly. It's like CSCI 40 all over again, right? So okay, we're gonna make a file that ends in .s. All right, we'll call it, I don't know. Let's not mess with these. I'll call it return in assembly .s. Okay, it's an empty blank slate now. So I'm going to give you a bunch of assembly instructions. The assembler, the thing that like creates object code out of the assembly, doesn't really care if they're lowercase or uppercase. I will save myself my pinky by making them all lowercase, but you can make them all uppercase, doesn't matter. Comments are just like C++, so you can use double slashes and the multi-line comment. But let me write code for you. Let me show you return 0 essentially in 64-bit ARM assembly. So here's what you gotta do. You gotta say where the program starts. So you say .global _ start. It's a special place. All right, we're saying that this exists now, and we're saying, all right, here it is, _ start, colon. Like from here onwards, this is where _ start, that section of the code begins. All right, but this first line is saying Anybody wants to know can know. Start as a global place. Anything with a colon is called a label. Start as a global label. All right. We'll get more experience with this soon, I promise. But like here it is. We can indent if we want. You can have multi-line comments. This is a multi-line comment. And I should probably make it actually multiple lines. There's our multi-line comment of the day. And let me show you how to return, I don't know, some special value. Let's return like 55 or something. Or let's do the 42. Let's do the 42. We'll change it. So what we got to do is we got to move into a special place called W0, the number 42. All right? So what this means is move 42 into a special place called W0. W0 is called a register. Into the register W0. So essentially, it kind of looks like a line of C++ if you squint. It's really doing that. It's saying W0 equals 42. It's essentially that line of C++. So W0 is a special place in the CPU. It's a special like variable. It's called a register. And then this is the return value. And then I want to move into a place called X8. That's another register. I want to move the special number 93 of all things. It's got to be 93. This moves 93 into the register X0. That's another place. Sorry, X8. It's another place. You can imagine that there's like W1, W2, X0, X1, X2. There's a few of them. But these ones are special. They got to be exactly those. And then we say SVC number sign 0. And that does it. Okay? So let's talk about that last thing. So what we're doing is we're setting up what's called a system call. All right? That's a way of us talking to the operating system. In our case, this is Linux. We're talking to the Linux operating system. And so we're going to give it a special code saying what we want to do. We want to do special thing number 93. So 93 is the code in the operating system. In 64-bit ARM Linux, it's the code for the exit system call. A system call is just a special thing that the operating system does for you. You ask it to do a thing. We're asking it to exit the program, right? So 93 is the exit system call, and then that system call takes some arguments placed in certain things called registers, special places in the CPU. So we're placing into W0 the exit code, and that's what the exit system call expects. It expects to see in W0 that exit code, all right? And then to make the system call happen, we've set everything up. We've given it the right code, given it the right arguments, saying to say, hey, go and do it now. We're ready. You say SVC 0. All right. And what this does, SVC stands for supervisor call, which is kind of funny. You're talking to the operating system. Your supervisor is the operating system. You're essentially asking to speak with the supervisor every time you want to do something fancy in any of your programs. So that's secretly what's going on, which is really funny. So this is saying, hey, Linux kernel, which is the operating system, please execute the system call that I just set up. All right, that's it. There's our program. That's our assembly program that returns 42. Okay, and okay. Our assembly instructions can be lowercase or uppercase. So there's one called add. You could have done add or add. So I did move. You could have done capital move. Doesn't matter. We did all these things. Now to make a runnable program, because again, this is just English looking stuff, we have to assemble it. There's no compiling anymore. There's assembling, all right? So we have to run what's called the assembler, and that's AS, all right? The assembler creates object code. So we say AS, give an assembly file, .s, and then we can have it output to some special .o file, whatever we want to call it. So this is called the assembler. It creates machine code, object code, for that one file. So we're going to run the assembler. We're going to say AS, return in assembly.s, -o, let's just call it return in assembly.o. It's going to be the machine code for that one file. And this is not yet ready to be run. It's just not executable yet. It's machine code. It's not ready. It's not a final program. To to finish it off, to make something executable, even if we don't have multiple things, we're not actually using any libraries right now, we're just talking to the kernel specifically, directly, you still have to run the linker. All right. So we're going to say the linker's name is LD. We're going to give the object code file, the .o file, and saying link it together with all the other stuff that I give. There's only one thing. It's just like make it executable essentially. Take this, make it executable, and call it whatever we want to call it. All right, that's the linker. It's the two-step process that G++ has been doing for us this whole time, but now we're doing it manually. All right. All right. We have this machine code. We're ready to link it into a final executable program. So take my return in assembly.o, create a final executable file called return in assembly. So there is my executable program now. So I went from this assembly code, object code, linked it to make this executable file, which I can then go and run /return in assembly. And if I didn't mess it up, ooh, we ran it, echo $?42. Isn't that glorious? So again, I don't expect you to understand any of this right now. This is just our first foray into assembly. I'll explain more all of these instructions in detail later, but now you know these are instructions. Every line is an instruction. Okay? There's no like semicolons in assembly, so they got to be on separate lines. Okay? So there's that. What else? Yeah, I think that's kind of it. Let's change it. Let's change it to not return 42. Let's have it return like 55 instead. Let's put into the W0 register the number 55. And so it's essentially doing this. It's saying W0 equals 55 in like C++ land. So to it's not compile anymore, it's reassemble. We have to reassemble with AS and relink with LD. Boop. And so now I'll rerun, return in assembly. And that should do it. Now we're returning 55 as the exit code of our program. So that's pretty cool. And that is our first taste of assembly. Hopefully at least it makes a tiny bit of sense, right? This is where we're going. So that's pretty fun. We're talking directly to the CPU, which is awesome. All right. So the next thing I want to do, like that's the lecture. That's the lecture for the day. With every lecture comes lab time. If like this were a normal class, we get like a 10-minute break. So like go pause the video, take a break. You're entitled to one. But let's do lab stuff. I want to get you on the class server. So let's get ready for that. All right. So let's connect to that class server right now when you're ready. All right. So it's going to be at server.lottensclass.com. That's the name of our server. And to access it, you want to, if you're on Windows, you can download what's the PuTTY program. Or if you're on a Mac, you have a terminal already. You can search for it. It's in your applications utilities folder, I think, if I remember correctly. And yeah, if you're on Windows, do PuTTY. Or you can install. You could go through, like there's a bunch of different things you could use. You could use PowerShell. I'm using Windows Terminal right now, and I can help you with all that. But PuTTY for sure will get you on there. All right. So I do want to say your accounts, PuTTY. So install that. Your accounts won't work until the first day of class. So if you're watching this video slightly early, just keep in mind your stuff not going to work for a little bit. Oh shoot, what just happened? I was trying to zoom in. PuTTY. I'd like to zoom in, please. There we go. Something weird was happening. So if you're on PuTTY at least, you do this. You say, I want to connect to server.lottensclass.com. Port 22 is the default SSH port. It's perfect. Have this SSH selected. It should be default. Then you hit open, and then I can unzoom. And then pretty much no matter where you are, it's going to say, do you trust the computer about to connect to? You say yes, I trust. And then you're going to type in your username and your password. And this is just like the class website. Your username and password, they're two separate accounts though. I do want to say they're two separate accounts. If you already changed your class website, www.lottensclass.com password, you still have the default one on the server. So your username and password are your last name _ student ID right now on the server too. Okay? Changing one account does not change the other. So that's that. So do that. So you're going to say login as who am I? You're going to say last name _ student ID. no underscores, no dashes, no special characters, and you hit enter. And then it's going to ask you for your password. And your password right now is the same as your username. All right, you're going to type it and hit enter. You won't see stars. Linux is super, super fancy. The terminal is super, super fancy if you've never done this before. It's extra secure. It's not even going to show you stars, so people over your shoulder can't even count the number of characters of your password. All right, extra secure. So you're going to type and hit enter and just pray. It will work. All right, you're going to say your password, which is the same as your username right now at the first login. I have already changed this one though. What was it? So you hear me typing. There are no stars, but it's getting it. Hit enter when you're done. And then if you're successful, it'll plop you here and it will force you to change your password. So you're going to type your current password again, then type the new one you want, and it'll have you confirm that. And then it'll kick you out. You'll come right back here with PuTTY. You'll connect all over again using your new password. And once you get to the cow, you were successful. Okay, so you're on the terminal on our computer, right? On our class server. If you want to log out, and I'll show those of you on Macs how to do it in just a second. If you want to log out, you can say exit or Control D when you're done. But keep it open. Keep it open for now. I want to show you some stuff. So exit or Control D will log you out. If you are on a Mac, open up your terminal program. And here's how you connect. You say SSH. There's a command called SSH. And then you say your username, last name underscore student ID. Then an @ sign like an email, @server.lawtonsclass.com. Hit enter. Again, it will probably ask you, do you trust this computer you're about to connect to? You're going to type yes, hit enter. And then it'll ask you for your password. And again, it won't show the stars as you're entering it. So you'll type it. Hit enter. It will get it. And again, it'll force you to change your password and it'll kick you back out to your own terminal. You'll just run SSH all over again to connect right back. All right? With your new password. And then once you get to the cow, you're in a good spot. All right? So, yeah, just let me know if you have any issues with that. Come to office hours. And please save your work often. This is a computer in Germany that we are connected to right now. Who knows when there will be a power outage? It's pretty good, but you never know. All right? I do want to say, you don't have to work on the class server if you don't want to. There is a slight lag because it has to cross the Atlantic as well as the continental US to get to this place. I swear this is the closest cloud provider with an ARM processor. So the things I do for you. You don't have to do your work there if you don't like it, all right? You just have to turn everything in on the class server, all of your laps. So if you want to copy files from the server to your computer, you can use a cute little program called CyberDuck. There's that one. You can download it from this website. Or if you're on Windows, there's WinSCP. That's a thing. WinSCP. There's that one. And I'd be happy to show you plenty of other ways to do it. So there's all those ways to transfer files. And I can help you get Linux on your own computer if you would like as a virtual machine. That's something I've done. And if you're feeling extra fancy, I can even show you how to emulate ARM Linux on whatever computer you have. If you have an Intel processor, I will help you emulate ARM Linux. Pretend that it has an ARM processor inside of it, which is super nice, and then you can do all your work there, and everything will be happy. Because the assembly language will be different if you're on an Intel processor running Intel Linux. We're doing it ARM assembly in this class. Okay, so yeah, let's talk about the shell, the terminal itself. If you have never used the terminal, I am so sorry. Again, this is something we require at Clovis, but I do have some optional reading for you if you would like. This Unix/Linux terminal command tutorial. If you click that and just read through it, that will teach you the terminal. But also, please come to office hours. We have to get you up to speed very quickly. Okay, so let me show you how to move around. So when you log in, you are plopped into a place called your home folder. You can the terminal prompt will tell you that. It's this tilde is short for your home folder. If you say pwd, short for print working directory, and hit enter, that's really where you are. There is a folder in the root directory of this file system, and there's a home folder, and inside of the home folder is a folder with your username, and that's your home folder. That's the place where you put all your stuff that belongs to you. Okay, there's that. And you can look inside of the folder where you're at. There's always the concept of where you are, your current working directory in the terminal. So I'm in my home folder right now. If I want to look and see what's there, I can say ls. So I actually have some stuff right now. Let me get rid of them all with the remove command. So for you should see ls and it spits nothing back out to you because there is nothing in your home folder right now. It's this blank slate. Okay, so you can put stuff here. All right, you can, first of all, you can make folders. Make it like a folder for your labs, make dir labs. And so now if I say ls, ooh, there's a folder here. And I can work inside of it. I can say cd labs. And now you see I'm in my home folder's labs folder, pwd. It went from this to this. So now I'm looking at the labs stuff. If I say ls now, it's an empty blank folder that I just made for myself. You see? It's empty versus when I was in my home folder, it showed me that the labs folder existed. If I want to go back out to my home folder, I can say cd tilde, or I can say, if I was in labs, again, I can say cd dot dot. That's always a shorthand for your one directory out from where you were. Okay. If I say cd dot dot again, you can see like all the home folders for everybody right now. There's only 3 accounts on the computer, but there will be eventually all of your accounts on this machine. cd tilde, if you ever get mixed up. cd slash, that's like the outermost directory. Can't go out any further than that. This is like the root directory of the file system. You got all these fun things. Okay, so cd tilde to get back to where you were. If you would like to edit a file, I will teach Nano to you, which is the disgusting terminal-based editor that's easy to use. If you've never used the terminal before, start with Nano. But I will hopefully instill into you the idea that Nano is just a crutch and you want to learn Vim. So to edit a file, if you'd like to make a file, let's make a hello world file, for example. I'll say nano hello.cpp. Hit enter, and this will open up the Nano editor and start editing a file called this. Hit enter. Of course, it's blank, but I can write a program. Start typing. Include iostream, using namespace standard int main. Gotta manually tab over cout hello world. New line, return 0. And then if I want to save this file, this caret character down at the bottom, it's showing you all the things it can do. The caret character means it's short for control. So if I say control X, it's save and quit. That's really what we care about right now. So if I type control X, if you're on a Mac, it is still control. It's not command X. Control X, it'll say, do you want to save this? Y for yes. And then what do you want to call this? Well, I want to call it the file that I used when I opened Nano. So it's already filled out for me, hello.cpp. Just hit enter to keep that. And now if I type ls to see where I am, ls is short for list, by the way, lists the contents of my current directory, I can see that hello's there. I can go back into it if I want. I can say nano hello.cpp all over again, move around with the arrows. It's all there. Control X to get back out. And yeah, if I want to compile and run, I can say g++ hello -o hello. That makes this executable file. And to run a program, a compiled program on the terminal, you say // name of the program. So there it is, hello world. And I can go back to Nano, name of the file I want to edit. And bam, I can change it around, do new stuff, recompile, rerun. That's my lightning intro to the shell. Please come to office hours, read that optional reading page if you need to know more or you haven't used the terminal before. I'm going to force you to get very good at it if you've never seen it before, so do mentally prepare for that. The last thing before we go, this is like our lab session right now. I'm not going to give you an actual assignment yet, but like an optional assignment if you feel like it. I have used Vim today and from now on. That's my editor. That's the terminal-based editor that I use. So I think it's the best editor for you to learn because it'll be pretty much on any machine that you SSH into in the future. Please, to learn Vim, do not say vim hello.cpp. It works the same. You do it like this eventually to edit a file. But do the Vim tutorial before you do this because you don't know how to exit Vim. It's :Q to exit Vim. It's very weird. So to learn Vim, what I encourage you to do is to run the vim tutor command. You say vim tutor on the terminal, vim tutor, and you hit enter, and it plops you into the Vim tutorial. You can start moving with the arrow keys, and eventually, as you read this slowly but surely, it will teach you the Vim way of doing things like, oh, instead of the arrow keys, use these guys, do this. How do you exit Vim? It teaches you that the first thing. You type escape, then you type :Q. If you've made changes, you have to include the exclamation point. That's what it's saying. But go through this thing. Go through Vim Tutor. It will save your life. Okay? It's great. All right, try to finish it with as much time as you have, because like your assignments right now are do this and then do that assigned reading. I think that's it. All right. So that was a whirlwind of an introduction. That was officially all that I have for our lecture and lab portion today. I hope you don't feel too overwhelmed. Please yell at me as much as possible on Discord. Come to all my office hours. I will be here for you to help. But I think that's where I want to leave you right now. So I will see you in the next lecture.